you. Thanks for the invitation. I'm very happy to be here. It's been really interesting so far. Yeah, I was asked to give a talk during this workshop. Um, and yeah, I want to say, yeah. So Eric told me two things when I was prompted that I was going to give a talk. First, it had to be something related to low D gravity. So I was not allowed to go to higher dimensions. So then I'm a little bit stubborn, so I will, but there will still be low gravity, of course, very commonly. That's the whole point. And then second was to keep it very open, very general, like very discussion-like. So I'm not going to talk about any specific paper. I will mention references. The things that I'm saying is inspired by stuff that I've been working on in the past few years. But mostly my task here is to give you a list of things that I am confused about and that I think are reachable, are doable. And so this will be very much like a discussion in that point of view. Okay, so you will be asking me, but what about this? And most likely my answer will be, I don't know, let's work it out. So this is basically my aim with this talk. And I think that Eric instructed me, but I instructed myself. I'm trying to for this. So that's why I wrote a few things in advance to just see like sort of like, because really like the things that I have to say are quite precise. I don't have to, if you start asking me questions, this is the only reason why I will stay here longer, which is great. But like, well, I think I encourage that. I encourage that you ask me questions, but I really try to keep it like to some very specific thing. They're not going to be like grand pictures. I'm not going to solve the information paradox or tell you what the black hole microstates are. No, this is, I'm a very simple person. I like to do very concrete things, and this is how I'm taking this approach, one step at a time, and then we'll build the grand cathedral of quantum gravity. Okay. As the title says, what I wanted to do is have a discussion on how to build a bridge between what we learn in low D gravity in a higher dimensional perspective. So this is very much, I'm basically following Christian's question at the end of the session on Wednesday. It's like, what do we learn about higher dimensional setups when we do all of these 2D computations? Okay, so this is the theme of everything that I'm going to be saying today. And in particular, the most obvious connection between what you do in low dimensions with high dimensions comes via the near-extremal black hole. So be something, I'm assuming that most of you are familiar with this, but I decided to write some equations just to kind of set up the stage and what is like the basic things that everyone knows about how for 2D gravity is related to near-extremal black hole. So the most famous example, the simplest one to describe very shortly and briefly, comes from the Rice-Ostrom solution in 4D. So even to be super explicit, this is basically a solution of Einstein-Maxwell theory in 4D. You can add, again, we can add cosmological variance, but just to start the discussion very mildly, like very gently, this is in something that is asymptotically flat. I even wrote down the metric for you of this black hole, where here I'm writing it for the non-extremal case, so you have an inner and an outer horizon. I decided the charge to be magnetic. It makes things a little bit simpler. You can put electric charge, you can put both. I will discuss examples with both, but like to keep it brief, you just have some magnetic charge. And here I wrote down how these R plus and R minus are related to what you call the mass of the black hole and the charge of the black hole. Notice here, I wanted P to not have units. And so that's why I have this funny factor of G4 here, just so you see exactly where G4 enters and what is quantized and what's not, okay? And so then this black hole has entropy, its area, it has when we talk about the near-extremal limit, we're basically very close to having R plus equal to R minus. Near-extremality means that you have some small difference that here I'm quantifying by some parameter epsilon. And G4 is what I'm using as my decoupling parameter, basically what will take me close to the horizon of G4. So this follows very much For instance, if you wanted to read this in a paper, there's the old paper of Michelson, Maldacena, and Strominger that basically sets up the problem in this way. Okay, so I'm basically following that same convention. So if you're exactly at extremality, so this is when R plus is exactly equal to R minus, you have this relationship between the mass of the black hole and the charge. This R naught here is basically the charge of the black hole. But when you go a bit away from extremality, so when you have this little parameter epsilon that basically turns on a little bit of temperature, the very famous result is that the mass responds quadratically with that temperature, and the entropy responds linearly with this temperature. And what we have learned in recent years, so these two parts here, what I'm describing at this stage, this is something that's very old. You didn't need it to do anything fancy. This is just black hole thermodynamics. And there's a quantity here, m gap, that I wrote here that goes like 1 over g Newton. And these formulas, if you want a way how to read them, is basically the statement that actually you can't keep this energy above extremality to be finite in the limit that you're taking g Newton to 0. So it's like the famous statement that you can't have finite energy expectations in ADS. But the coupling limits that we do, like in higher dimensions, you can have with energy expectations inside of ADS, and it's because the coefficients that go here that don't depend on that decoupling parameter. But this is basically the problem of ADS2, because when you take these decoupling limits in the geometry is basically, when you zoom in, basically it's ADS2 central. What have we learned from a low D perspective about these quantities? So what you can do is basically, so that line element there you can generalize and write it in this fashion. Okay, I'll keep the magnetic charge exactly the same. That's also why I picked it magnetic. And what you can do here is a dimensional reduction, a K reduction, where I'm keeping just the S wave sector, meaning I'm not putting any extension in the sphere, as this answer illustrates. And these variables here just depend on the transport part. So this is the RT, if you want, directions of the space-time. And if you do that dimensional reduction on that action that I wrote down there, you get this effective action, okay? And when this effective action falls into the universality class of what people will call, depending on who you are, you will put it in the bucket of like JT gravity generally. I don't know, like it's probably, you don't know what I'm talking about, but basically, sorry, this is R2, not R squared. Basically, what you get is a theory that has the 2D metric as your D2, as your degree of freedom, and then the size of the sphere here appears as a dilaton in your action. And where you see JT gravity specifically is basically, so this dilaton has the property that if you set it equal to a constant, basically the solution that you get, so this phi naught, and that's also why I introduced it here, just to normalize it correctly. This is the solution that you would have set I. It's exactly ADS2, so you're here at the bottom of the throat. But if you allow this field to fluctuate, and I'll call the fluctuations Y, just to have a different symbol, and you look at what happens to the linear order in Y, then this theory is exactly JT grav. Okay, so with this, you get JT grav. Okay, so that's the old story. This is how you see JT gravity showing up in the physics of near-extremal black holes. Now, I'm doing this for the specific example, but in general, what happens if you go to different dimensions, if you change the cosmological constant, if you do various other things, the intuition that you have in mind is that the size of the sphere here is basically what you're calling the JT mode. And then this is your effective description. So it's basically telling you this near-extremal limit, basically when you move a bit away. This is part here. And now going back to the thermodynamics, what does this effective description here? So now you have basically an EFT for the black hole in 2D. And the beautiful thing about this theory is that this theory captures basically, so JT gravity actually captures this thermodynamic response. Okay, so that's something that you can show very carefully and very precisely. And basically this M gap here is related to basically a background values that you give to Y. So there's a very explicit relationship between what M gap is doing and the fact that you had Y different from 0. And furthermore, something that was very surprising was that this theory, this JT gravity theory, also tells you something about what happened, not just semi-classically, but it also tells you something about the quantum correction to the black hole. Okay, so it also tells the near extremality. There's also a very important one loop correction in the temperature that basically has that 3/2/2, and the 3/2 is basically coming from 0 modes that you had, the 3 0 modes that you had in the 83 and up. Yeah. This is an excellent, I don't know, question for the future. So this is, so usually here the metric, okay, in general, like I don't necessarily have to say that the future is real, but okay, like, I don't know. So this phi is basically R squared. And so I tend to like my radial coordinates to be real, but this is exactly the type of question that we need to ask, because of course what's happening nowadays is that there's a lot of emphasis here, and then we forgot where this came. And that's the whole point of what I want to discuss today. It's like, let's remember where this is and how we're supposed to connect things back. But this is an excellent question, because there's also a lot of non-perturbative things that happen here. I have no idea what they say about the rising Austin black hole. Someone has something that they can teach me about that, that would be it. Mm-hmm. If you were, you had to expand, here I'm doing it exactly. So just expand this up to linear order. Even away from, sorry, so you're saying, and this is the, okay, this is what you get explicitly from dimensional reduction. And then you can just expand around this point and then see what are the terms that happen. And this is something I will discuss in a moment, about how do we understand what those expansions do, which is something I don't know, but it's something that you can do very systematic. But yeah, at least the first correction is just JT. But then, yeah, this exactly, like you get this 1/5, 1/5 cubed, 5 squared here. This is, I'm not doing in this expression. I just did a KK reduction on a CFT. That's all I did. Right. Yes. Yes. This come exactly as you set up the gravitational pattern. I think all of these questions, because yeah, even back in the 70s, like a problem, we haven't solved it. We just normalized it. That's the only thing that has happened since the original papers when people were looking at the Euclidean path integral. So we just feel very comfortable with rotate. But yeah, so far, I think we haven't learned any. This will be interesting to, again, revisit. I think, unfortunately, yeah, my attempt is to make everyone embarrassed. We still don't have anything new to say about that. Okay. Oh, he's asking about the P-tube. It's it's actually it's an interesting question. I wasn't going to talk much about this. What enters an M gap? There's numerology about it. In some sense, something had to enter, and like usually what enters is the ADS2 scale. It depends a little bit. The only thing that you also have to be careful. So these are dimension full quantities. So you do have to be careful how you're measuring temperature. And so, and for different situations, there might be like different choices. So here, my definition of temperature is like the same as the one that I'm using from the 4D point of view. But yeah. But it's basically it's controlling so this it's controlling your ADS2 rates. It usually ADS2 radius is going to come in here, and you can really do that because of how you're expanding this effective action. But if other quantities show up, that which could show up, that's a little bit like a case sensitive. So it's not like I can something like this, like the G4 is always there, but like the very specific dependence here, it's something that okay, you just compute it and you see what you get. But it does, you have to be careful. Yeah, how do you define this? Because yeah, it's dimension full again. So you can hide some things depending how you cast stuff. And in particular, you can hide them inside of the temperature. Yeah, if you map, yes, you can. There's no inconsistency. But of course, you have to be careful. Like when you define this Y, you basically match it to the response that you get from here. So what you're doing is, so when you take the near horizon limit, so this thing exactly, it's R squared for that solution. And so then what you do is you basically expand, you say, this is R naught plus something that will look like this times an ADS2 variable. And then you have to decide. So usually because this is a square, there's also another R naught. Sorry, this is R naught squared, and then plus dot, dot, dot. And so depending on how you define the radial coordinate in ADS2, it tells you like what is the prefactor that goes up here, that tells you what is what. All matches up, but there's a little bit of like sort of like how do you choose your coordinates? It's not a very meaningful like I don't want to dwell on it too much, but basically if you want to be kind of like hand wavy, you can say it's the ADS2 radius that controls the map. Yeah, like if the details are not important. But it is something that you do have to. It's dimension full, so it's not something that it's like extremely like set in stone, like a sensitive charge, let's say. Let me maybe let me it makes in a different way. So there, I was trying to favor G4, so that so let me write it in a different way, and maybe this will be more illuminating. So if I replace P4 for L2, look like this. And that has the right unit. So it's L2 cubed. But then here it's kind of awkward, like my statement that if you take G4 to 0, you don't get energy, it doesn't work, right? So that's why I like to write it like this, because then it's obvious that ADS2 can't support energy, because then it comes from the top here. That's all. And there's a factor of 2 pi if you want to be that. But like from a dimension, like if you wanted to guess like what, okay, so you have G4 that has units. of distance squared, and then you wanted to guess like, how do I make something that has units of length? Okay, you can write it like that. And there we go. Yeah. Yeah. They're massive modes. Yeah, exactly. So the S-wave sectors are consistent truncation. And so any solution of this theory will be a solution of to these equations of motion. It is a equation. But you can keep also the infinite power K modes that come from the sphere. And then there will be more terms. They won't they don't affect any of these statements so far. Yeah. Yes. Mhm. That's an excellent question. At this level, so if I just have this toy model, you would say basically like so in comparison to this part, because it happens where they take the approach of like so for instance, like a lot of work that Iliescu and Kuriachi did, they took the point of view of the 4D path integral. Okay, so when they reproduced this result in particular, you might have been suspicious because this result was known from the point of view of like, the Schwarzschild action that comes from JT gravity. But then you might have been like, but do I really see it in 4D? And so what these guys did, they did grab this action and they said, let's go around this geometry. So they looked at the gravitational path integral around here, and they see that it actually, this path integral at low energies is basically governed by the same massless mode. And it gives also the 3-has velocity. So you can also see it from 4D without doing this dimensional reduction explicitly. Like if you didn't know about JT gravity and you only wanted to know about 4D physics, you can also reproduce this. Well, perturbatively, you can always do, I do know how to do a one loop computation in 3D gravity. This comes from a one loop computation, very close to extremality. And so I don't need to do like a very fancy path integral. I just basically have to think that I'm allowed to. And then when you do a one loop correction, you have to understand what are the different massless and massless, sorry, massless and massive. And then basically heating correction and temperature is this one again. Yes. So here I'm being a little bit I'm going to like in a specific like fixed key ensemble. You can make, so just for simplicity. So and this is also why I picked magnetic charge, because it's very easy to, if I impose spherical symmetry, then it's very simple to freeze this from the point of view of the consistent truncation. From the point of view of the gravitational path integral, you can turn on a chemical potential for it and then be either in canonical or microcanonical ensemble with respect to P. So you can be at fixed P or a fixed mu potential, and you can do the path integral in either way. There will be zero modes also associated to this F, and you can compute those as well. But yeah, just trying to. Yeah, you do have to be careful. Yes, there's some modifications here depending on which ensemble you are. Right now, I wrote the answer for the fixed charge ensemble. So in these equations, I'm fixing Q and seeing what is the response of the system at fixed Q. And I should also say there are also zero modes associated to the sphere. So I don't know why I wrote S2 down there. That's awkward. And there's some zero modes coming from the two-sphere, but and that depends also if you're like, you can also think of like that you could have perturbations that add a little bit of angular momentum, and so you can decide like, do I have a chemical potential for those angular momentum expectations or not? But there's also things that you can do in that regard. But yeah, like the thing that is like, I just wanted to have this part here that clearly comes from that low D. And in the original in these papers by Lesher and Kuriachi, they do discuss these different ensembles and what happens to those fluctuations as well. We do see that. That action is enough. Yeah, the 3/2 just comes from the ADS2. It's because you have 3 killing vectors here. So this is like directly like, okay, that's it. Yeah. Okay, so this is the background. This is this like the state of the art. This is basically 2016, roughly. Well, these guys, this 3/2 is 2020, roughly. So that's where we are in the time around 2016 and 2020. Now, what I want to illustrate is, and basically motivated by questions that I already had, and in connecting it to this low D perspective, 2 questions that I think are important, so I'll write them here. And so the first thing that I wanted to discuss more in detail is about building this effective, this EFT and T. Okay, so I have shown to you a really, really simple example, like the most spherical cow is what I've written in the Blackboard. But I want more. So because I have in mind other cows, and as we will learn, they have spots. Okay. And so because you might think that this is it. If I'm just really, really good at JT gravity, then I know everything about quantum black holes. And I do want to say that the answer is no. And there's really basic evidence saying that the answer is no. Okay, without doing very fancy computations, just asking the question. Yes, it did, but there's something even worse. So I want to even be more dramatic about this, because how Tolia's question, I said it doesn't matter, right? Do the 4D computation or the 2D computation, you'll get the same answer. That's Tolia's question, and I want to illustrate that was an answer. So thank you for. I gave you a really shitty answer, Tolia. It's a true answer for that theory. But there's more than just Einstein Maxwell in life. I hope we can appreciate that. And then the other thing that I want to, this will be more vague and discussion related, is that, and this is actually something, yeah, at different stages of my life, I've been thinking about this. Like I've thought about this with waves for super, super long. I'm getting confused. Last month, I was talking to Per about this as well. And you know what? We've been terrible at connecting observables in this discussion. The only thing that I know very clearly to connect between this 4D picture and this 2D pictures are things like this. And I'm going to make a big rant that's roughly where it stops. And I will show you like what type of computations I would like to see connected between the low dimensional perspective and the higher dimensional perspective. Okay, I'm not going to provide answers. The second part is literally me ranting like a crazy lady here. Okay, and you can prepare your questions appropriately. Okay, so let's move on then. Oh, this is super smart. We just go like, so then, okay, great. Okay, so the point is first point building T, but one you guys should ask if this can be got a little bit less. That's all. Let's keep back to the Pascal Institute. Okay, so let's talk first about that. Building this ESP. Okay, so what I have done, sorry. Okay, so what I've done so far, about universal aspects of these near-extremal black holes. Okay, so what I have illustrated that blackboard on the top is things that basically an extremal black hole. There's of course always a when you say all of them, but basically this is, you haven't seen like something different here, but this is usually your vanilla kind of behavior. But what I want to right now is about non-universal aspects of these extremal black holes. Okay, and how do you build this effectively? And concrete, since I'm going to be a bit rushed because how am I doing in time so far? I do want to beat my record. Okay, it's been 35 minutes. This is based, what I'm going to tell you now, it's a paper that we wrote in 2021 with Edita Verhanden. I'm mispronouncing her name terribly. Sorry, Edita. But so we wrote this paper, and this paper was very naive at the moment. We were just like trying to understand, like, can I see basically what are what is this S wave sector for a certain black hole? So the setup is going to again have in mind uh, 4D black holes that will be of the rhizome type. They will carry both electric and magnetic charges. So by rhizome type is going to be exactly of the form ADS2 times S2. So I'm not even going to add any rotation. So this is just the simplest setup. But what we decided to do was to say, let's embed this in n equal to supergravity. Because I'm old-fashioned, and I was taught that supergravity was a nice theory to study black holes. Okay. And so let me tell you in a summary, what do we do? So let me start first. So there were two cases that we looked at. And so let's first do what's called STU, which is an ungauged theory of supergravity, where the cosmological constant, you don't know what ungauged means, the cosmological constant is 0 in 4D. So we looked at black holes and this theory. ST and U is that I'm going to talk about right now. This basically means that when I write down my 4D effective action, I will have basically three complex scalars that come from like the vector multiplets that the theory has. It doesn't matter. Basically, think of them as fixed real scalar. T and U is basically the name of each of the matter. So this is going to be a supersymmetric version of that Einstein theory. So you will have three complex scalars, and you're also going to have basically a bunch of this gauge fields. So instead of having one, you have four gauge fields. Okay. Now, in this theory, the black holes, the metrics look very, very similar. If there's things like there. But what happens in this theory is that basically you have, when you characterize the black holes now, can carry electric charges and magnetic charges, many of them. So this index is going from 1 to 4, the 4 gauge fields that you can have. And there's an object here that is called the Cayley hyperdeterminant. I'm not going to write it, it's long. But basically, this is an object that the entropy is as a function of it. So it's the area of the horizon, if you wish, when you're at extremality. So let me say the entropy of the extremal black hole is basically the absolute value of this determinant. And what happens to this determinant, the reason why we like, in supergravity, people like to characterize solutions by this determinant, that 2 branches of solutions. So you can have a non-BPS branch when this delta 4 is negative, and you can have a BPS branch when this delta 4. So it's a nice way how to understand if this solution is supersymmetric or not. You can have extremal black holes that are supersymmetric, and you can have extremal black holes that are not supersymmetric. Okay, great. So seems all well and fine. And so then we said, okay, let's build this theory. So let's build the EFT, which will be a consistent truncation. Just to be emphatic, for me, these things are synonymous, but just very clear, it is actually a consistent truncation. When you have these 2 cases, and the new computation here, not a computation, but the new is that when you look at the, so this is in the S wave sector again, is that if I have a truncation, I need to look at the fluctuations of those scalars. Okay, so those are also to give me modes that are in the S wave sector. Okay. My 2D theory is going to look like what I had before there. So it's going to look like something that will have like JT gravity, okay, in it. But then there's going to be basically kinetic terms for this scalar, okay? And then we also look at what happened in terms of coupling between the scalar and the field. So if you want, this is just like the pure gravity sector. Then you will have kinetic terms for the scalars here, and then you're going to get them also interacting because this thing is nonlinear. So there's going to be interaction. Okay. So this above here. But now let's look at what happens just looking at the spectrum of fluctuation in these 2 cases. Yes. Mm-hmm. Well, for the purpose of what I'm saying now, I just want something that really describes things like all the mathless expectations that I could have. So that's what I meant by EFT. But then I do want it to reproduce the same physics that I had in 4D. So that's why, so yeah, but that's why I'm taking them as, for the purposes of what I'm trying to say now, equivalent statement. So. Not yet. No, I'm just reduction of like the theory. That's all I'm doing. You terms gravity theory that has here has kinetic terms. So I'm just dimensionally reducing these terms. In this dimensional reduction. So maybe I should also be more clear. So I'm doing it. Well, you don't have to put here A as 2 times as 2, but just because I wrote down JT gravity plus things, and you can view it as an extension around the IR physical. But yeah. So I'm doing like the dumbest, like KK reduction that you might have thought this is going to be really boring. And I was just bored, and I just needed to compute some fluctuations as I went along. So so let me just illustrate what happens in each. So if you go into the BPS branch versus going into the non-BPS branch. So first of all, the spectrum of these fluctuations that you have here. So you basically put these scalars. So there's 6 of them. So each of them will have a little mass associated to them. And they will also have, I will write things in terms of a conformal dimension. So, and it's a conformal dimension with, so I'll tell you what the values of delta are, which are related to the masses that you get in this fashion. And here, every single conformal dimension that you get for the scalar is basically equal to 2 for these kinetics. Here, what you get, you basically get the following type of spectrum. So you get a delta that is equal to 0 for 2 of them. Let me divide it like this. You get delta equal to 2 for 3 of the scalars. And you get delta equal to 3 equal to 3 for 1 of the 6. Okay, so this one is time shift. So what do I want to illustrate with this first round of like simple examples? So let's break down. So there's JT field here. So there, I also have this in both theories. Of course, I have y as a fluctuation, and the conformal dimension that you associate to y is 2, and the ADS2 lambda. So that's why it's an irrelevant operator with conformal dimension 2. This is the thing that makes the theory break conformal symmetry, and so in the BPS, everything is at 2 or higher. Well, I'm looking just at the S wave sector, so everything starts with 2. And so basically everything that I said up there, it will still hold, will still be fine. Okay, because the most important massless contribution that will come these computations is basically this field that I have here. But now you can see from here, I get an operator. Sorry, delta was 0. This is stupid. It's mathless. Sorry, it's delta equal to 1. I get basically here a margin off. So these are marginal. And these 2 are irrelevant. This one also has a nice interpretation. It's basically, if you view the solution as coming 5D, this is a Khalifa-Klein direction from a 5D perspective, but you basically have a marginal deformation. This is telling you also you have a flat direction in the attractor mechanism. If anyone of you remember what the attractor mechanism was, this is where you can see generational differences. Attractor mechanism, people don't know what it means, but basically, this is a reflection of flat directions in the pattern. And so there's this marginal difference. You will say, fine, this is information do well too much. Shouldn't stress about it. Yeah, because I'm adding, so I have what I have, but I make it perspective. So you get skin. What's that? Everybody gets the y because, yeah, because you always have a sphere. So y, that capital phi is the mode that you get from the sphere. So that's consistent no matter how I do the, no matter the black hole. So that part is the universal part. But here came something that made me go into a rabbit hole, because then we looked at what happened to the couplings, those cubic interactions that you have in this theory. You're always going to have, because phi comes as a determinant of the metric, you're always going to have terms that are going to look, sorry, let me write it in terms of y. You're always going to have something that will look like y parts of your scalar. Okay, so this is a cubic interaction that you will get generic. You always have cubic interactions here. So now I told you this thing, and let's look at what happens for this case where I have delta equal to 1. So this is a guy that has conformal dimension 2. And here I have two operators that have conformal dimension 1. 2 is equal to 1 plus 1. Another old-fashioned topic of ADS-CFT. This is an extremal coupling. No, you get tons, but this is the one that made me panic because when you get couplings that are of this form, you can't compute Witten diagrams easily. They explode. They never show up. In this case, that you will never have this because 2 plus 2 is 4, and then it's not 2. So you can see in the BPS branch, you're fine. You never have these type of coincidences. If you can try to manage them, but they don't. And here also, for instance, if you look at like you could have said there was also, you could have feared that there would have been a coupling that was 1 plus 2 equals 3. It doesn't show up. But this 1 plus 1 equals 2. The extremal here has nothing to do with the poles, but basically this is an extremal coupling in ADS-CFT. And yeah. And this made me think briefly about from the point of view of EFT, what do you do in ADS-CFT when you have extremal coupling? Because in ADS 5 times 5, they don't show up. In ADS 4 times 7, they don't show up. In ADS 3 times 3, they also don't show up. And people have written conjectures about vanishing of extremal correlators as like some grand principle. But this is just to illustrate. You start playing around and you see some cases break the lore. If you want to know, keep things brief. I don't want to dwell on this, but I do have an answer on how do you deal with it. So this is pathological. If as written, just so you know, this is pathological. You try to do a computation, it blows up. So you have to renormalize it, and it's highly non-trivial, and then understanding the physical implications of that renormalization. So far, yes. So we did renormalize it. We don't see what's the mention. Yeah, no, it's something peculiar about how Y is being in JT gravity. But if Y would have just been any other field, not the JT field, so any other operator from conformal dimension 2, you do see an anomalous dimension. So it's making the 3-point function, there's a log that shows up. And we're interpreting it as an anomalous dimension. And it's a correction. So you basically have a degenerate spectrum, and you have to let that mixing between single trace and multi-trace operators. But it's kind of peculiar. I think this is just things that break, like actually start looking at explicit examples. And so that's one thing. Now, yeah. So there I have to be, so we didn't see anything else. So for this guy here, so for instance, these two guys don't have a cubic coupling. So at least at that order, we didn't see anything else that was mixing. The only thing that was giving us a cubic coupling so far in the theory was this. Everything else is like higher KK. And so it's not going to be that you're not going to have the coincidence that 1 plus 1 is equal to 2. You might, yeah. So what we did is we just basically tried to make sure that that right there gave a reasonable answer. Like, how do you make that fight? And that, damn it, took lots of work. That was kind of not tricky. Because there's no literature in it. There's not a single example of ADS-CFT that has this extremal coupling. It's just that in this, But here the coupling is not zero. That's the point. Oh, we need to add counter terms because here, this is a case where boundary counter terms are finite. And that's why there was also this puzzle of extremal correlators in the literature of ADS-CFT. People thought in the CFT, these correlators are non-trivial, and how do you reproduce them from ADS if the bulk coupling is zero? And the point is that you get, this is a case where boundary terms are finite, and this is because extremal correlators, even when they're not renormalized, they suffer from ambiguities that you can redefine the operator by multi-trace, basically, contribution. So you can, and so this gives you an ambiguity on like what exactly the extremal correlator is, because you can always redefine the field. So there's always a basis in which the 3-point coupling is zero, even in the CFT, if you pick the right coupling. So like Marika Taylor had these papers in the case of ADS-3 times 3 that was nice, and then Rosselli years later also clarified this for the case of ADS-5 times 5. You can always go to a basis where those couplings were zero. But if you wanted to use a basis where they're zero, it's because there's boundary counterterms that are finite. And that's how, but when we're doing that, so we add a boundary counterterm, but it's cutoff dependent. And so you're also breaking, so what we're seeing right now is that in the expectation value of the stress tensor, you get like a matter anomaly contribution to the stress tensor, and that's the part that I'm trying to understand how to interpret it. So I'm kind of going to stop there. But what we have achieved is basically have, from the gravitation point of view, a renormalized action that is finite. And that was already not feasible. So hopefully it will come out soon. Yeah. That's why I wanted to be a little bit careful. So in the computation, because you actually treat it as a background field. So because that's what's making the theory kind of like run. And so for computations, this guy, you have to treat it as delta -1. This is like the shadow. But it's still, it still gives you trouble. Like it doesn't help you, because you get divergences either with this. So in the ADS-CFT in general, like you will get problems if this is true, or if let me get it correctly. What's that? No, why is it not dual to the stress tensor? The stress tensor are the torsion modes. Those are your gravitons. It gives life to the Schwarzschild description. So that's why you get like that's why like the M gap is basically controlled by Y. But it's not the gravitons, it's like, and it's that expectation value, like the fact that I added that information there. And it gives me just a coupling around which I'm doing conformal perturbation theory. So that's how I think about it. But because, yeah, so you put some value, like you added a bev to the thing, and then when you're doing this type of computation, you view it as there's intermediate steps with okay to treat it a bit dynamical, but then at the end of the day, when you get the final result, you have to put its background value, and then if it was an operator from a dimension -1, because B -2 is you can see it from the this comes because of the you have flat directions in the tracker mechanism. We expect all the scalars to have a fixed value at the horizon, and where you're looking at the there's two scalars that are not fixed. Yeah, you can view it like, so when you're describing the mod, the non-BPS branch, and you tell me find a solution to Einstein's these scalars, like constant, there's two that are not fixed by the equations of motion, but they can be whatever they want. And it's because the effective potential that you have just has like two flat directions in it. And this was, they're all papers by Trivedi and collaborators, where they noticed that in non-BPS cases, you do have flat directions in the attractive mechanism, and they were trying to interpret it from the modularized versions from theory. But they're non-BPS cases, so it's not very easy to know exactly what's there. But from the two derivative theory, you just see that at that tractor, so at this near horizon, the equations of motion don't fix the scalars. It can be whatever they want. And that's why you get that the fluctuation, you have two marginal deformations, because you can move around, you can pick any value for a scalar, and you will still be at the conformal point. In the BPS case, you don't do that, which is great. So I'm reassured. If I would have gotten here delta equal to 1, I would clearly have been wrong. Because we know that the tracking mechanism is robust. Okay, so I'm going kind of slowly. So let me use the same blackboard. So let's do now ADS4. This is more, okay? So maybe you didn't care about this. Let's do ADS4 black hole. It's not, it still has the same number of scalars, but my supervisor told me it's not STU. So although there are papers that call it STU, so I'm supposed to call it, this is U1 to the 4th supergravity with n equal 2 charge, which is a representation of n equal 8, SO8, sub SO8. Any case, you still have 3 complex scalars, you still have the 4 gauge field. Of course, you don't have this determinant, so let me not write this for this case. But you do still have a BPS and non-BPS black holes. And you can again construct this effective theory. And let's see what happens here. So I think in view of time, the non-BPS is actually worse, as I'll say in a few seconds. But let me say something about the BPS case. Yes. Yes, they do. They're the consistent truncation of an 11-dimensional complexification. So I'm heatless. I'm not doing anything exotic. This is actually the most plain complexification that you can have. And these are, and now in this case, in this BPS branch, I'm going to be talking about a black hole that is the black hole that was discussed by Benini, Christoph, and Zaffaroni. So actually, even this is a black hole for which we know how to reproduce the entropy from the index. So let's do this academic exercise of figuring out what are the fluctuations around this black hole. Why not? Because I ABGM, right? And I can say many things about ABGM or someone else, not me personally. Okay. Have it written down here. So this black hole, the PS black hole here, I'm going to look at magnetic version. So usually you characterize it by integers. Each of these integers is basically, so it's going to be something, sorry, just to not introduce more notation, it's going to be something that looks like the absolute value of lambda 4 times whatever magnetic charge has. And I'm going to be looking at a case where N1 is equal to N2 and is equal to N3. And then there's a supersymmetry condition between them that N1 plus, sorry, N4 was equal to this. So N1 plus 3 times N4 is equal to 2. So if you want the solution to be supersymmetric, you need to impose that condition. The most supersymmetric, this is a supersymmetric. The compute the deltas, and what you get is the following. So I'm expecting 6 operators, and so I'll draw it. So I'm here, so I'll draw it as a line, and I'll just give you the expression for one of them. So you can see what the dependence is. So I can start with operators. So here, 0, 1, 2. This is where my delta. So I still have the delta y in this cases. I always have the JT field. And there's basically 2 operators that sit here between 0 and 1. There's how many? There's a bunch that sit. There's 3 of them that sit here with different conformal dimensions. So this one is times 1. This one is times 1. This one is times 2. And then you have another one that sits here. So for supersymmetric black holes in ADS4, in terms of your spectrum, you get 10 deformations. You get deformations that are between 1 and 2, that's still irrelevant, between 1 and 2. And you get also some relevant deformation as well. Now, why? And just to give you, maybe let's write down the expression for one of them. All of them have like the same they all have like this funny square root showing up, but like some of them have things subtracted and that's what just said. So first remark, the deltas are functions of the charging. The conformal dimensions that you have are functions. What point of view of it? The conformal of these are also operators, single trace operators in APCM. In the UV, the conformal dimensions of these guys, I hope I'm remembering correctly, it's 2. And so there's a non-trivial RG flow where the values of the conformal dimensions depend on background charge. So homework number 1, can someone compute this in the CFTC? I've asked some experts, apparently it's doable, but I haven't seen it done, and I need someone to do this. So there's a prediction here, you have ADTM, where you get these conformal dimensions down to. And so, and get this explicit dependence. Okay, yes. Oh, okay, sorry. So that's a nice computation to do if you like to do symmetric theories and you like to basically understand what is the quantum mechanics in ADGM that describes these black holes. Okay, do that. But second, so if you were around 2016 and were very excited about the Maldacena-Sanfillan paper, and you went down to the appendix, there's something called Appendix D. Want to know what happens in Appendix D of Maldacena-Sanfillan? Okay, so in Appendix D, it's called when the Schwarzschild does not dominate. There are some, yeah, this delta is between 1 and 2. And 4 is negative. Yeah, sorry. And 4 goes, this goes from minus infinity to minus 1. Sorry, we just decided to put that way. So, and yeah, it's because of this constraint. So we picked in 1 positive and then N4 has to be negative. Yeah. So, any guess? The portion does not dominate. It's basically, so in this, they show that this portion is not going to be the prominent effect if you have an operator that is in this window. They put 1 here because their computation breaks down when delta is exactly equal to 1. But I have 3 operators that will actually even be below 3 hashs. The function should not dominate in this model. The supersymmetric black hole is the one that these guys match it to the index. It's exactly the same one, the same theory. So what do I do with it? Nobody has taken computing the gravitational path of the. The response with temperature of the effective action. If you compute the effective action when you have operators with this conformal dimension, then this I effective goes like temperature to the 2 delta minus 2, and the Schwarzschild has temp, this goes linear with the temperature. Well, it's a classical action. You do have to turn on a source for the mode. So it's just the action. So you do basically the field with its sources. And yeah, it's like you just grab you grab this, and but why am I not supposed to, like, K does not have that. So nobody has talked about this, and they say it in their paper. It's like K just have operators in this window, therefore remove all hat along, because who doesn't like SYK? SYK is, but this is like limitations of like, what if you say something about black holes? Because when I have black holes in ABS4, for which we pretend to be really good at understanding what the microscopic nature is, it does not resemble SYK because you do have operators, and I don't have a field theory reason why I should not be turning on these operators before turning on this one. These are deltas with respect to ADS2, so CFT1. So this is a CFT1. So here, PV, this delta. Yeah. So from the point of view of the ADS4 integer conformal dimension, but then when you flow into the CFT1, it has a conformal dimension that depends on the charges in this way. Things I've been told that maybe if you do some F extremization, I extremization, then maybe you can see why there are symmetry went to something that is like non-trivial as a function of the charges. I never seen something like this. Sometimes people have seen that the conformal dimensions maybe changed by an integer or something, but I never seen something that has like this kind of non-trivial square root behavior. I wanted to write it explicitly, like this is not like it's like plus n4. And then you say, but n4 is okay. This is an irrational number. So you would have to say that the right structure in the infrared is something which like these primary. So also to be clear, these guys are chiral primaries from the point of view of ABDM. So the flow of those chiral primaries is something like trivial when you put the theory on S2 times S1 and with a non-magnetic flux. No, it's homework. So this is homework. Yeah, yeah. I want to have a better understanding of like what am I supposed to do with these operators, as I'm trying to describe the behavior of the black hole away from externality. Yeah, you should include them. You should, but then I also want to then have a better understanding, because in the supersymmetric case, you still have a mass gap. So should I have a better estimate of what the mass gap is? There's a computation here to be set. So I'm just, I don't know, it's not clear to me that the 3/2 was the most important thing that you have focused on. And so I want a more careful analysis of the DPI in cases where you do have these other operators that are supposed to be more important. And from the quantum mechanics point of view, from an SYK-like model, it also, these guys, they're going to show up, they're there. So it's like, so how does this help you also in trying to build some SYK-like model for these guys? So, so yeah. So what time? It's late. It's late. Okay. Are you sure? Okay. This is at least very, just so you know, do this. And also say, last year, no, 2 years ago, 2022, this type of effects get conformal operators whose conformal dimensions are either between 0 and 1 or below. Yeah, basically having operators here was also something that was noticed by Horowitz, Polanski, and Santos. Because when you look at the gravitational spectrum, you also get an ADS4, an extremal ADS4 black hole. You also get a lot of operators here. But that's not in the S-wave sector. You do need to look at like the higher modes. But it's kind of robust in ADS4 that you always have operators here in the system. But supersymmetry doesn't save you. That even in supersymmetric cases, you also have operators equal to 0. Good question. Yeah, we have to do a computation section. This is just a kind of dimensional analysis computation. So do this carefully. Tell me if yeah. What is really like the effective description as we move away from the finale? And I'm two theory features of that. So, okay. And so then maybe the last thing that I was going to say, I'll move on now. So this is to illustrate what happens when you actually start deciding doing computations and saying like, let me have a 2D theory. Like the story, the big rough here, it's an important, regardless of these extremes, is that as we're trying to what quantum gravity is, it's important to add matter. And so what I'm illustrating here is what is the matter doing and how can it maybe deviate that were sort of so dominant in the just gravitational sector of this low D field. So I'm providing some features of like, this is what the matter should be doing in these cases, and then maybe how it might be addressing some of that we find problematic about the two models in the absence of. Okay, so that's what you're supposed to. This is what you're supposed to take off. Okay. No, not that. Well, Julian is not good, but it would be nice if he. I don't see it in their papers. Yeah. So I think that in about some of, not Julian in particular, he's great, but I've seen other papers by other authors that, for instance, they say, let's do JT gravity plus matter. Okay. And then because it's really easy to do massless field, they just pick the massless case there. Couple the massless field with the JT mode, they just couple it to gravity. And from a higher dimensional point of view, I would say, but wait, this thing, if it's from a higher dimensional point of view, you land in this problem that I was having. And you have it extremal correlate. This is, nobody talks about that. They add matter. They don't like to add that third term that I had there. That they just say, it's the matter coupled to the metric, to the 2D metric, and that's where it stops. But if you're coming from a higher dimensional, those couplings are just there. And if you like massless fields because it made the computation easier, well, there you have an extremal coupling because again, 2 is equal to 1 plus 1. Ignored. There will be more massive modes. I don't see how okay, maybe I'm being a bit too naive in my Wilsonian approach. I don't see how the massive modes are going to cure this. But if someone tells me, like, actually, if you look at the entire cosine tower, you're not doing something that should be okay. I haven't seen any evidence when I'm doing computations that I should do it. But this comes to my last point of like connecting observables. Like, because then also I can do a lot of computations in 2D and I don't know how to interpret. And I think this will basically connect very well with what you're saying, also what Tolia was asking. Something that has been not done is connecting actually the observables that you compute in this IR fixed point to observables that you would compute in the asymptotically. So whatever you compute here, how do you connect it to a computation that you did here? And that will also illustrate, did you actually capture the relevant physics? What was the EFT that you wrote here? Is it actually something that really subtly, like solidly captures that? And so let's move to that very fast. I don't have as much to say. I'll just say things that bother me. And so you can erase it now. And this is where I'm going to get close to it. And we'll keep that picture. So there's actually also in there. So now we're going to be talking about observables. In the past, I know of 2 computations that do something along the lines of what I'm asking for. The 2 examples that I know that are beautiful papers, and I'm very lucky that one of the authors is here in the audience, are the following. So what I want to do is basically either if I have here Minkowski 4 or ADS-B, so let's write down here Minkowski B. Okay, pick your favorite dimension. I basically want to relate observables deep in the throat to observables in the asymptotic. Okay. And so what are the examples? There can be more. These are just the ones that I know. So the first one comes from a very nice paper from 2010. Where it was not ADS2 what was in the bottom, but it still illustrates the point. So it was an RG flow between ADS3 times R2. So this computation where they basically showed, so in ADS3, there's some similar flavors of safety gravity, where you have these boundary gravitons of the Rossero mode. And what I liked about that paper was that it illustrated how the boundary gravitons here became typical from the point of view of ADS5. And it made that connection between like the CFT2 physics that you have here with the CFT4 physics that you have there. So that's what. Cool. And then the other example, and matter, and it's also to work of Shoxen and collaborators, not right, but this is from 2011. This is in the case something in Minkowski 6. Do again something that is of the form ADS3 times S3 horizon jump. So here in this case, what they showed is basically that the boundary gravitons that you have here connect to PP waves in Minkowski 6. Now we know what PP waves is. Yeah. I actually had to look it up. Yeah, do you want to know what I didn't know what it meant? I know what it is, but I didn't know what. plane wave parallel propagation. Very, it rolls out of your tongue like this. I had to look at it. I think the PP is just a parallel propagation. I think Wikipedia did not say why it was just 2 P's and not 3. But basically here, yeah. So here you have boundary gravitons, the Brown-Hinault boundary gravitons. And it's kind of nice to see that like something that was a pure diffeomorphism in ADS3 became this PP wave here. So they become dynamical. So they become dynamical gravitons from the point of view of Minkowski. So this is a beautiful, the paper, if you open it, this is not what they stressed, but this is the part that I like about the paper. They were trying to understand microstate geometries in D1 and 5. But the lesson that I took from that paper is basically this one. Now, for everything that I've been talking about now, we don't have that same picture. I don't have like that same connection. And this is where, just to end the discussion, I want to illustrate, for instance, computations that people do in the 2D theory around the JT gravity point. And the homework is, can you tell me what that computation means from the 4D perspective? Okay, so what is a computation that someone would do in 3D? So from the 2D JT gravity plus matter point of view, so this is described also in the original papers. You will look, for instance, at like the 2-point function of some operator of conformal dimension delta. So you will grab some matter field, it will be dual to some operator, and you will say, compute the 2-point function of that, right? And so then this 2-point function, how would it look like diagrammatically? So you will get one term that I'll write it like this. So this is basically the 2-point function at finite temperature. This is the thing that you would interpret from the point of view of the CFT1. I can write the expression. I want to what you get, like the sign or the finch of beta is the periodic part of the correlation function. Okay, so you just look at what correlation functions in the ADS2 background are. You get that. Then you can say turn on this JT mode, and I'm turning on gravity. And so then you can have a correction to this correlator because you're doing the computation where you have basically y as a background. I'm just illustrating there that y is like a background field. And so you have it as a source. And so that you can have a correction to the 2-point function. And then if I parameterize this, so this is going to go something like a number divided by the distance, but basically this is the thing that comes at order A. If you do the computation, this is thing that you can reproduce in SYK. Okay, SYK has like a counterpart computation of this, and you can see that what you get in gravity is the same thing that you get in the SYK. And then there's another correction that is basically the graviton. So you have the O here and the O here. And this thing over here is going to and this thing is the correction to the 2-point function. Here you can describe the mode. Okay, so it's within a change of fraction, and there's an explicit expression, and it's given by that. Okay, and then you have more corrections. So I'm doing a small expansion here. I don't know how, so this one I know how to interpret from the 4D point of view. So this is the 2D perspective. Good. This computation, or too high. This computation here, in my old-fashioned way of thinking of this is the gray body factor computation. How many of you have done? So old nowadays. It's like, what? So this is how kids, this is how ADHD is discovered. We had gray body factor computation. So what people did, you guys laugh, but it's true. Go back to an ID, you were computing gray body factor, so throwing things at black holes, doing a reflection and transmission coefficient, and they saw that they looked like a CFT. That's the computation. You get gray body. So from the point of view of gray body factors, it's clear like, what you're getting here, there's a matching condition, and you see how things, you discover this IR. Other two, I personally forget. Been related. So things that you see, for instance, here, when you also put it in the 4-point function, related chaos and exponents and things, but I haven't seen a computation where you start in 4D and these corrections, number of dimensions. But I might be missing something important. I don't know if it makes a question or not. I'd like to know if I'm asking the wrong thing, and then maybe I should keep doing these computations in 2D because they're not the right thing to do in 4D. But this is where I would like to know, what am I supposed to extract? So if I do computations in 2D, what am I supposed to learn about like the 4D difference? So that's, but again, this is where it's very open, and someone can tell me, Alejandra, go read this paper, or this is the just so that I become less ignorant next time I give a talk like this. Practice, yes. Yeah. Exactly. Yes. Good. And then there's also a small little caveat that I don't know if it's important or not. We're planar black holes. And I think that's kind of important in a way that I understand. So yeah, and I would love for someone to illustrate that in those computations. Even in this ADS, like a flat space is a little bit more complicated because you would have to relate it to an S matrix perhaps or some other observable. But in ADS4, I think this is, I would love more explicit. I was reading some of the SCMT papers, but like because yeah, you have here R2 instead of S2. It just didn't kind of hint it to the same physics. I think it's still there, but I didn't things that were like, it's yelling at me these two things. But maybe again, I would love to know where should I look at so that this part, of course, is there in that discussion, and it was great. But these other two, I don't. Okay. Uh-huh. Okay. Okay. That's okay. It resembles this one. Okay, but this one, not yet. Well, but it's the one that is supposed to give you all the chaotic part of it's the gravitonic change, right? That we're saying this is where chaos comes in. So Yes, sure. I yeah, I didn't see it. Yeah. Yeah, this one maybe like this part here, I think I know the paper that you're referring to. It has this part very explicit. I I was struggling to see this, but that's what they claim in the abstract, and I failed at seeing what was happening. This one I haven't. They don't talk about it. That's for sure. But this one, yes, they claim that they. I to be honest, like I okay, we can talk about that paper a bit more because I'm failing to get the text back. But again, it might be uh, my next. Yeah, it sounded to me like, I don't know. Okay, I'll stop there because which one? The middle one is basically, so you grab that cubic interaction, and you compute it. Basically, the computation that you do is, so the 2-point function will get corrected by something. So you have what you had before, and then there's an integrate. This guy is the background PI. And so that's why you care about what those cubic couplings are. And that's why I also freaked out when this thing extremal, because then I couldn't compute it. And that's the computation. The delta is of the operator you have. You pick your favorite. Yeah. Yeah. So just pick a field that you have in the book and you compute it sequence function. What time? After I finish my paper, then you will be able to do the cycle 2 one. But right now, if you do it today, you'll get a big fat infinity because this thing is not well defined. I like our naively is not well defined. Yeah, but it's also the gravitonic spin. But that's all I meant. It's coming from the Schwarzschild part. For the 4-point function. But for this one, I would like to see, yeah. Yeah, that's why, like, yeah, the 4-point function, there's a counterpart from the point of view of those stock weights. I would like to see, in general, like, I think that we should be doing more of those type of comparisons. So there's a few cases, but I think it's too few. And there's a lot of computations people do in 3D, and then it's really difficult to then understand, like, this is what I learn about it from a 4D point of view. But yeah. So that's why the only reason why I said like chaos is because I'm having the gravitonic and you know, it's a bit and with this, I'm basically I'll stop here. This is it. So or not, it's also fine. See, yeah. I'm yeah. It was a like trying to think about fragmentation. I don't have anything useful to say. I think it's an excellent question to ask. Uh, what is if there's a useful way from the 2D point of view of characterizing fragmentation? So I've talked to Tarek about it quite a bit and some other collaborators, and I'm yeah. Where I promised that I would say like you guys would get someone questions, I'll be like, yeah. I think it's an interesting thing yeah, it would be very nice to know. It's difficult because then, yeah, you don't quite get it. Like you do have to take into account that you did have two centers, and then you want to basically understand from the 4D point of view, like how do you write something effective there, but where you can still see the features of JC. Or if you deform JC, a way that we are trying to think about is that if I'm inside of one of the throats, what would be a mechanism that will like take me to the other? And then I don't know, you might think that that's also non-perturbative, and so then you can't view it if you're just in one. So I'm still I don't know if we have to pick the right language and just that to be acceptable. Let's go for lunch. Okay, let's go.